Picture this moment. You're standing at a launch pad. In front of you, a spacecraft. This isn't just any ship. It can reach 99.9% the speed of light. You step inside. You say goodbye to your family, your spouse, your 5-year-old child. "I'll be back in 1 hour," you promise. The ship launches, accelerates, reaches that incredible speed. You check your watch carefully. Exactly 60 minutes pass, 1 full hour, then you return home. But when you step out, everything has changed. Your family, gone, not dead, just older. Your child is now 30 years old. Your spouse has grey hair. You have grandchildren, because, on Earth, 25 years have passed. You lived 1 hour. They lived a quarter century. This isn't science fiction. This is Einstein's special relativity. Proven, real, unavoidable. In the next 90 minutes, I'll show you exactly how this happens, why it happens, and what it means for humanity. Fair warning though, after this documentary, nothing you thought you knew about time will ever be the same. Let's begin. Part 1. The Impossible Journey. Imagine standing right there, right at the edge of everything you know. In front of you stretches a massive launch pad, metal gleaming under floodlights, steam rising from cooling systems. And the ship. This isn't some ordinary spacecraft. This machine represents humanity's greatest achievement. A vessel capable of reaching speeds that shouldn't exist. 99.995% the speed of light. Think about that number for a second. You're about to move faster than anything in human history. Faster than imagination itself. The hatch opens. You climb inside. The cabin smells like new electronics and recycled air. Your heart pounds against your ribs. Behind you, on the observation deck, your family waves. Your wife stands there, 33 years old, holding your daughter's hand. Your little girl is 7. She's wearing that yellow dress she loves. The one with sunflowers. "When are you coming back?" your daughter asks through the intercom. You smile at the camera. 1 hour, sweetheart. Just 60 minutes. "I'll be home before dinner." Your wife nods. You can see she's nervous. But she trusts you, always has. 1 hour, she repeats. "We'll be waiting right here." The hatch seals. The countdown begins. 10, 9, 8, 0. The engines roar to life. The launch that changes everything. Acceleration presses you back into your seat, not painfully. The ship's systems compensate perfectly. But you feel the power. The raw energy pushing you forward. 10 seconds in, you're already moving at 10,000 miles per second. 30 seconds, 50,000 miles per second. 1 minute, you've left Earth far behind. The planet shrinks to a blue marble in your rearview displays. 2 minutes. Solar system landmarks blur past. Mars, the asteroid belt, Jupiter's massive form. The acceleration continues. Smooth, relentless, beautiful. At 5 minutes, something incredible happens. The stars ahead of you start changing color. Blue shift. Pure physics in action. Light waves compress as you rush toward them. Stars that were yellow turn blue. Stars that were red turn yellow. Behind you, the opposite occurs. Everything shifts toward red. You're experiencing the Doppler effect at relativistic speeds. 10 minutes into the journey, 90% light speed. The universe transforms. Ahead, all the stars compress into a brilliant tunnel. A cone of concentrated light. Everything to your sides vanishes into darkness. Not because the stars disappeared, because light can't reach you from those angles anymore. You're moving too fast. 15 minutes. 99% light speed. Inside the cabin, everything feels normal. Your coffee still tastes like coffee. Your breathing remains steady. Your watch ticks at regular intervals. But outside, time and space are twisting into shapes that defy description. 20 minutes, 99.9%. Here's where the real changes begin. On Earth, your wife checks her watch. Strange, you've been gone for 7 hours already. 7 hours when you promised 1 hour total. She calls Mission Control. When is he coming back? Mission Control looks confused. We're seeing the same thing. According to our calculations, he's experiencing extreme time dilation, but we assured you this would only take an hour his time. What does that mean? She demands. The scientist on duty goes pale. It means Earth time and his time are different. Very different. The mathematics nobody warned you about. Let me explain what's happening while you're still accelerating. Time isn't universal. Never was. We just lived our entire existence, moving so slowly we never noticed. Albert Einstein figured this out in 1905. He was 26 years old, working a boring job at a Swiss patent office, reviewing applications for new inventions, coffee cooling on his desk, and suddenly he realized something nobody in human history had understood. The speed of light is constant, always, for everyone. Sounds simple, but it shatters everything. Here's why. If you shine a flashlight while standing still, light leaves that flashlight at 186,000 miles per second. If you shine a flashlight while running, light still leaves at 186,000 miles per second. Not faster, not slower. Exactly the same. If you shine a flashlight while traveling at half light speed, light still moves away from you at 186,000 miles per second. Impossible. Your brain screams, yeah, mine too. But experiments prove it. Over and over. So if light speed is constant, something else must give. Something has to be flexible to make the math work. That something, time itself. Einstein called it time dilation. Time stretches. Time compresses. Time becomes elastic depending on how fast you're moving. The faster you move through space, the slower you move through time. Picture a cosmic budget. You have a fixed amount of velocity to spend. You can spend it moving through space. You can spend it moving through time, but the total never changes. Move fast through space. You crawl through time. Stand still in space. You race through time. 25 minutes into your journey, you reach maximum velocity on your chronometer. 25 minutes have passed. On Earth, 12 years have disappeared. Your daughter isn't 7 anymore. She's 19, starting college. Her childhood is gone. She barely remembers your face. Your wife is 45 now. Grey streaks in her hair. Laugh lines deeper around her eyes. And you've aged 25 minutes. The return that breaks your heart. The ship begins its turnaround. The massive engines rotate. Deceleration starts. 30 minutes. You complete the outbound leg. The ship has executed a perfect 180. Now you're heading home. Same incredible speed, same physics, same time dilation. From your perspective, everything seems fine. The cabin temperature holds steady at 72 degrees. Your sandwich tastes fresh. Your muscles don't ache. But back home, time keeps rolling forward. 35 minutes, your time. On Earth, another 5 years pass. Total elapsed 17 years. Your daughter graduates college, gets her first job, moves into her own apartment. She talks about you sometimes. My father disappeared when I was 7. Some kind of space mission. They said he'd be back in an hour. 40 minutes your time, Earth time 17 years becomes 22 years. Your wife celebrates her 50th birthday. Friends ask if she's dating again. No, she says quietly. I'm still waiting, but doubt creeps in. Everyone tells her you're not coming back. The mission failed. You're dead. Move on. She refuses. 45 minutes. Another 5 years on Earth. Total 25 years since launch. Your daughter is 32. She's married. She has a 2-year-old son. Your grandson. A child you've never met. The landing nobody prepared for. 55 minutes. Final approach begins. The ship enters Earth's atmosphere. Heat shields glow orange. 60 minutes exactly. Touchdown. The engines shut down. The cabin goes silent. Your mission computer flashes green. Flight complete. Duration 60 minutes. Status nominal. You unbuckle. Stand up. Stretch. Your joints crack slightly. 1 hour of sitting. Nothing major. The hatch opens. Sunlight streams in. Warm. Familiar. You step out onto the pad, and everything stops. The launch pad looks different. Older. Updated. New buildings surround the area. The observation deck has been remodeled. A crowd gathers. Cameras flash. News drones hover overhead. An elderly woman pushes through the crowd. Silver hair, lined face, eyes filled with tears. Is it really you? She whispers. You stare. Something about her seems familiar. The way she moves. The shape of her eyes. I'm sorry, you say. Do I know you? She covers her mouth. Tears stream down her cheeks. It's me. It's Sarah, your wife. The world tilts. This woman is 58 years old. But your wife is 33. You saw her an hour ago. Except you didn't. How long was I gone? You ask, though you already know the answer. 25 years, she sobs. You promised 1 hour. But it's been 25 years. A younger woman approaches. Early 30s. Professional clothes. Carrying a toddler. Dad, she says tentatively. You look at her, at the child in her arms, at the wedding ring on her finger. Amanda, your voice cracks. My little girl, I'm 32 now, Dad. This is your grandson. His name is Marcus. You reach out with shaking hands. The boy looks at you with curious eyes. He doesn't know you. How could he? Your daughter's face shows joy and pain and confusion all mixed together. You're exactly as she remembers from childhood photos. Young, unchanged. But she's lived an entire life without you. I was only gone for 1 hour, you whisper. For you, your wife says. But we lived through every single one of those 25 years. Every day, every month, every birthday you missed. Every night I wondered if you were ever coming back. The crowd watches in silence. This moment is being broadcast worldwide. The first confirmed case of extreme time dilation in human spaceflight. You did exactly what you set out to do. Traveled for 1 hour. Came home safely. But the cost, your daughter's entire childhood. Your wife's youth. 25 years of memories and experiences you'll never share. The reality nobody can escape. This isn't science fiction. This is Einstein's special relativity. Proven mathematics. Unavoidable physics. When you move at extreme speeds, time genuinely slows down for you. Not metaphorically, not approximately. Actually, every watch, every clock, every atomic decay, every heartbeat, everything moves slower when you approach light speed. From your perspective, time flows normally. You don't feel different. Your 1 hour really is 1 hour for you, but compared to everyone else, you've skipped ahead, jumped forward, left them behind. Think about the implications. Right now, particles called muons are demonstrating this principle. They're created in Earth's upper atmosphere by cosmic rays. They travel at 99.9% light speed, their natural lifespan, 2/millionths of a second. At their speed, they should only make it about half a mile before decaying. Basic math, but they reach the ground 10 miles below. How time dilation? From our perspective, they live longer because they're moving fast, 22 times longer than they should. From their perspective, if particles could have perspectives, the distance to Earth's surface shrinks. Space itself compresses. Same result, different reference frames. GPS satellites prove it too. They orbit Earth at about 8,600 miles per hour, nowhere near light speed, but fast enough that time dilation matters. Their atomic clocks run 38 microseconds per day faster than clocks on Earth's surface. Engineers have to program corrections into the system. Without accounting for time dilation, your GPS would be wrong by 6 miles after just 1 day. After a week, completely useless. The universe doesn't care about our intuition. The speed of light is constant. Therefore, time must be flexible. And if humanity ever builds ships capable of reaching these extreme speeds, everything changes. Interstellar travel becomes possible, not just theoretically, actually achievable. Want to visit Proxima Centauri? It's 4.2 light-years away. At extreme relativistic speeds, you could make the journey in 90 minutes of your time. Of course, everyone on Earth would age for 0.2 years while you travel, plus another 4.2 years for your return trip. You'd be gone for 3 hours. They'd be gone for 8.5 years. Every journey into deep space would be a one-way trip emotionally. You could return physically, but everyone you knew would be older, changed, different. The stars are within reach, but the price is heartbreaking. So ask yourself this: would you take that journey? Would you sacrifice 25 years of your loved ones' lives for 1 hour of exploration? Would you trade your daughter's childhood for a glimpse of the cosmos? These aren't rhetorical questions. If we achieve these speeds, humanity will face these choices for real. Time travel exists. Forward only. No returns. No do-overs. 1 hour for you. 25 years for them. That's the bargain. That's the reality. That's special relativity. And nothing can change it. What we've just experienced is only the beginning, the setup, the scenario that makes it real. But how does this actually work? What are the equations? What did Einstein discover that made this possible? And more importantly, how do we know this is true? In the next section, we'll dive deep into the science, the mathematics, the proofs, the experiments that confirm every single detail of this impossible reality. Because understanding time dilation isn't just about accepting it exists. It's about grasping why it must exist. Why the universe has no other choice. Part 2. Einstein and the foundation of the theory. 1905. Switzerland. A small city called Bern. Inside a cramped office on the 3rd floor of the Federal Office for Intellectual Property, a young man sits at his desk. Papers scattered everywhere. Coffee stains on documents. A window overlooks a quiet street. His name? Albert Einstein. Age 26. He's supposed to be reviewing patent applications, evaluating whether new inventions deserve legal protection. It's boring work, repetitive, but Einstein's mind won't shut off. While other clerks focus on their paperwork, Einstein scribbles equations in the margins, thinks about light, about motion, about the fundamental nature of reality itself. And in this unremarkable office, during stolen moments between patent reviews, he's about to change everything humanity thinks it knows about the universe, the problem nobody could solve. For decades, physicists had been wrestling with a contradiction, a puzzle that refused to make sense. The question seemed simple. What happens to light when you move? Here's the problem. Imagine you're on a train moving at 60 miles per hour. You throw a baseball forward at 40 miles per hour relative to the train, to someone standing beside the tracks. How fast is that baseball moving? 100 miles per hour. 60 plus 40. Basic addition. Now imagine you're on that same train. You shine a flashlight forward. Light moves at 186,000 miles per second. The train moves at 60 miles per hour, basically zero compared to light speed, to someone standing beside the tracks. How fast is the light moving? According to common sense, 186,000 miles per second plus 60 miles per hour. But experiments kept showing something bizarre. The light wasn't moving faster. It was still moving at exactly 186,000 miles per second. Not approximately. Not close enough. Exactly. Scientists tested this repeatedly. Different speeds, different directions, different conditions, always the same result. Light speed never changed. The scientific community was confused, frustrated. Some proposed that space was filled with an invisible substance called ether. Maybe light traveled through this ether like sound travels through air, but nobody could detect the ether. Nobody could make the math work. Einstein approached the problem differently. The insight that changed everything. Einstein asked a radical question. What if everyone has been making the same assumption? What if that assumption is wrong? The assumption that time flows at the same rate for everyone, everywhere, always. Think about that for a second. Throughout human history, we believed time was universal, absolute, fixed. 1 second in London equals 1 second in Tokyo equals 1 second on Mars equals 1 second anywhere in the universe. Common sense, right? Einstein said, what if it's not? What if time itself is flexible? What if different observers experience time at different rates, depending on how they're moving? Sounds insane. But look what happens when you accept it. If light speed is constant for everyone, and you're moving toward a light source, something has to give. Either the distance changes, or the time changes. Einstein realized both change. Space contracts. Time dilates. The universe reshapes itself to keep light speed constant. This is special relativity. The theory that demolished our understanding of reality and rebuilt it from scratch. Let me show you how it works. The speed of light is the boss. Picture space-time as a fabric. Not just space, not just time. Space-time, a combined entity. You're always moving through space-time. Always, even when you're sitting still. Your total velocity through space-time is constant. It equals the speed of light. Wait, you're thinking, I'm sitting still. I'm not moving at light speed. You're not moving through space at light speed. But you're moving through time at light speed. Every second, you advance 1 second into the future. That's movement through time. Now stand up, walk across the room. You're moving through space. 5 miles per hour, but your total space-time velocity hasn't changed. You're still moving through space-time at light speed, total. So where did that 5 miles per hour through space come from? It came from your time velocity. You're moving slightly slower through time now, not enough to notice. 5 miles per hour is basically nothing compared to light speed. The time dilation is microscopic, but it's real. Now imagine you're moving at half light speed. That's 93,000 miles per second. You're spending half your space-time velocity budget on movement through space, which means you've only got half left for movement through time. Time slows down for you by roughly 15% compared to someone standing still at 90% light speed. Time slows down by more than half. An hour for them becomes 26 minutes for you at 99% light speed. Time slows down by a factor of 7. Their hour becomes your 8.5 minutes at 99.9%, factor of 22. Their hour becomes your 2.7 minutes. The closer you get to light speed, the more extreme the effect becomes. The mathematics made simple, scientists use something called the Lorentz factor to calculate time dilation. It's named after Hendrik Lorentz, a Dutch physicist who helped develop the mathematics. The Lorentz factor is just a number, a multiplier. It tells you how much time slows down at different speeds. At 0% light speed standing still, Lorentz factor equals 1. Time flows normally. At 50% light speed, Lorentz factor equals 1.15. Time moves at about 87% normal rate. At 87% light speed, Lorentz factor equals 2. Time moves at half speed. Their 2 hours equals your 1 hour. At 99.4% light speed, Lorentz factor equals 9. Their 9 hours equals your 1 hour. At 99.995% light speed, those 9 nines we mentioned earlier, Lorentz factor reaches into the hundreds of thousands. Their 25 years equals your 1 hour. The formula itself doesn't matter for understanding the concept. What matters is the pattern. Small increases in speed near light speed produce massive increases in time dilation. Going from 99% to 99.9% light speed doesn't just triple the effect, it multiplies it dramatically. This is why approaching light speed becomes increasingly difficult. You're not just fighting physics, you're fighting the structure of space-time itself. The proof in the sky? Show me evidence, you're saying. Prove this isn't just theoretical. Fair enough. Let's look at cosmic rays. Every second, particles from deep space slam into Earth's atmosphere. These cosmic rays create cascades of secondary particles. One type, muons. Muons are like heavy electrons. They're unstable. They decay rapidly. In a laboratory, a muon at rest lives for exactly 2.2 microseconds. That's 2 millionths of a second. Then it decays into other particles. Now here's the interesting part. Cosmic rays create muons in the upper atmosphere, about 10 miles up. These muons travel downward at 99.9% light speed. Let's do the math. At that speed, a muon should travel about half a mile before its 2.2 microseconds run out. Then it decays. So muons created at 10 miles altitude should never reach the ground. They should decay at 9.5 miles altitude. But we detect thousands of muons at sea level every single day. They're reaching the ground, all 10 miles. How? Time dilation. From our reference frame on the ground, the muons are moving so fast that time slows down for them. They don't live to 0.2 microseconds from our perspective. They live about 48 microseconds. That's long enough to travel 10 miles. From the muon's reference frame, if particles could have reference frames, their lifetime is still 2.2 microseconds. But the distance to the ground isn't 10 miles. It's less than half a mile due to length contraction. Same result, different perspective. The muons prove Einstein right every single day. But there's more. The satellites that depend on it. GPS satellites orbit Earth at about 12,500 miles altitude. They're moving at roughly 8,600 miles per hour. Not relativistic speeds, not even close, but fast enough that time dilation matters. Each satellite contains an atomic clock, the most precise timekeeping devices humanity has ever built. Accurate to within 1 second every 300 million years. These clocks broadcast their time to your phone. Your phone compares signals from multiple satellites and calculates your position. The system requires ridiculous precision. Light travels 1 foot in about 1 nanosecond, 1/1000th of a second. If the satellite clocks are off by even 30 nanoseconds, your GPS position is wrong by 30 feet. Here's the problem. Due to time dilation, those satellite clocks run 38 microseconds per day faster than clocks on Earth's surface. That's 38,000 nanoseconds. Your GPS would be wrong by 6 miles after just 1 day. After a week, completely useless. But GPS works perfectly. How? Because engineers program the corrections into the system before launch. They adjust the satellite clocks to run slightly slower. When the satellites reach orbit, time dilation speeds them back up to exactly the right rate. Einstein's equations are embedded in the GPS code. Every time you check your location, you're using special relativity, not metaphorically, literally. Your phone wouldn't work without understanding time dilation, the twins who prove the point. Now let's talk about the twin paradox. It's not actually a paradox, but the name stuck. Imagine identical twins. Let's call them Marcus and Diana. Both are 30 years old. Marcus stays on Earth. Diana boards a spacecraft. She travels at 99.5% light speed for 5 years her time. Then she turns around and comes back. Another 5 years her time. Total journey, 10 years for Diana. She returns home, steps off the ship. Marcus is now 50 years old. 20 years have passed on Earth. Diana is 40 years old. Only 10 years have passed for her. But wait, someone always protests. Relativity is supposed to be relative. From Diana's perspective, Marcus was the one moving. So shouldn't Marcus be younger? No, here's why. The key is acceleration. Diana accelerated. She changed velocity. She turned around. Acceleration breaks the symmetry. Special relativity only applies to constant velocity motion. When Diana accelerated, general relativity kicked in, and general relativity says the person who accelerates ages less. Not a paradox, an asymmetric situation. This has been tested. In 1971, scientists put atomic clocks on commercial airplanes, flew them around the world, compared them to atomic clocks that stayed on the ground. The flying clocks were younger, by exactly the amount Einstein's equations predicted, down to the nanosecond. The question nobody wants to ask. So here's the uncomfortable truth. Time isn't what we thought it was. It's not universal. It's not absolute. It's not even consistent. Your time is different from my time if we're moving at different speeds. The concept of now becomes meaningless. Your now and my now can be different moments depending on our relative motion. Two events that appear simultaneous to one observer might not be simultaneous to another observer moving at a different speed. Reality itself becomes relative. This bothered Einstein. It bothered a lot of physicists. Some still struggle with it today. But the universe doesn't care about our comfort. The experiments are clear. The mathematics is solid. The evidence is overwhelming. Time dilation is real, and if you move fast enough, the effects become dramatic, life-changing, civilization-altering. Think about what this means for space exploration. Right now, the fastest spacecraft ever built is the Parker Solar Probe at its peak. It reaches about 430,000 miles per hour. That's fast. Really fast. About 0.06% light speed. At that speed, time dilation is negligible. Completely unnoticeable in practical terms. But imagine we build a ship that reaches 10% light speed. Suddenly time dilation becomes measurable. A 10-year journey for the crew might be 10.5 years for Earth. Not dramatic, but noticeable at 50% light speed. A 10-year journey for the crew becomes 11.5 years for Earth at 90% light speed. A 10-year journey for the crew becomes 23 years for Earth at 99.9% light speed. A 10-year journey for the crew becomes 223 years for Earth. The crew returns after what feels like 10 years. Everyone they knew is dead. The world has changed beyond recognition. Technology is different. Politics is different. Culture is different. They're strangers in their own future. The trade-off we must face. This is the bargain the universe offers. You want to explore the galaxy. You want to visit distant stars. You want to see what's out there beyond our solar system. Fine. The technology is theoretically possible. Build a ship capable of reaching extreme relativistic speeds. But you must accept the cost. Every journey outward is a journey forward in time. You can visit other worlds, but you can never truly come home. Home will have moved on without you. Your friends will be older. Your family will be changed. Your world will have evolved, and there's no going back. No time machine to reverse the process. No way to reclaim those lost years. Forward only. One direction. No returns. Some people say this makes interstellar travel impossible. Not technologically impossible. Psychologically impossible. Who would choose to leave everything behind? Who would sacrifice their relationships, their connections, their place in time for a glimpse of the stars? Others say humanity will adapt. We always do. Maybe future space explorers will view time differently. Maybe they'll accept the trade-off as necessary. Maybe the call of discovery will outweigh the pain of temporal displacement. Or maybe we'll find another way. Maybe we'll discover something Einstein didn't know. Some loophole in the laws of physics. But right now, with our current understanding, the trade-off stands. Space versus time. Distance versus relationships. Exploration versus home. Choose one. You can't have both. The foundation is set, so now you understand the basics. Einstein's revelation, the constant speed of light, the flexible nature of time. You've seen the proof: muons, GPS, satellites, atomic clocks. The evidence surrounds us. You know the mathematics without needing to see the equations. The Lorentz factor. The relationship between velocity and time dilation, and you've confronted the implications, the twin paradox, the one-way journey into the future, the impossible choice between stars and home. But we've only scratched the surface, because time dilation isn't just about moving fast. It's about gravity too. It's about the warping of space-time itself. And when we combine all these effects together, when we look at what happens at the most extreme speeds possible, the universe reveals patterns even stranger than what we've discussed so far. In the next section, we're going to take that journey ourselves, step by step, minute by minute. We're going to experience what happens when you actually climb aboard that spacecraft and accelerate too, 99.995% light speed. We'll watch Earth fall away. We'll see time diverge. We'll feel the weight of what it means to move through space-time at the edge of possibility. And we'll understand, truly understand, why that 1 hour journey costs 25 years. Not as abstract math, as lived experience. Are you ready for the ride of your life? Part 3. The Personal Journey Simulation. Let's make this visceral, real, personal. You're not watching anymore. You're living it. The year is 2024. December 15th. Monday morning. You're 35 years old. Your wife, Rebecca, is 33. Your daughter, Emma, just turned 7 last month. Your son, Jake, is 4. You're standing in the crew preparation facility at Kennedy Space Center. White walls, sterile lighting, the smell of recycled air and coffee. In 6 hours, you'll board Horizon 1, the first spacecraft capable of reaching 99.995% light speed. Your mission, simple on paper: travel outward for 30 minutes at maximum velocity. Execute a turnaround. Return for 30 minutes. Total elapsed time for you, 1 hour. Mission Control has calculated everything. Fuel requirements, navigation vectors, life support systems, emergency protocols. But there's one calculation that keeps haunting you. Due to time dilation, while you experience 60 minutes, Earth will experience approximately 25 years. Your crew psychologist explained it yesterday. Used charts, graphs, equations. None of it prepared you for what it actually means. The goodbye that lasts forever. 10 a.m. The launch is scheduled for 4 p.m. Rebecca sits across from you in the family meeting room. Emma colors in her princess book. Jake builds a tower with blocks. Do you have to go? Rebecca asks quietly. Not for the first time. You nod. We've known about this mission for 3 years. The training, the preparation, everything leads to this. But 25 years? Her voice cracks. The kids will be older than us when you get back. Emma looks up. Daddy, why can't we come with you? You kneel beside her. Because this ship only has room for 1 person, sweetheart, and it's dangerous. I need you and Jake and Mummy to stay safe here. When will you be home? 1 hour for me. But for you, you struggle with the words. How do you explain temporal mechanics to a sec? It's going to feel like a really, really long time. Jake's tower falls. He starts crying. Rebecca picks him up. I'll be 58 when you return, she says. Emma will be 32. Jake will be 29. We'll have lived entire lives without you. I know. Your throat tightens. But this is what humanity needs. Someone has to test this technology. Someone has to prove we can do this. And it has to be you. You don't answer. Because the truth is complicated. Yes, it has to be someone. The mission is crucial. But does it have to be you specifically? Maybe not. But you volunteered. You trained. You committed. And now, 6 hours before launch, the weight of that commitment is crushing. The final hours, noon, medical check, blood pressure, heart rate, neural scan, everything nominal. 1 p.m. Final briefing. Mission director walks you through the timeline again. Minute 0, launch. Minutes 0 to 10, acceleration to 90% light speed. Minutes 10 to 15, acceleration to 99%. Minutes 15 to 25, acceleration to 99.9%. Minutes 25 to 30, final acceleration to maximum velocity. Minute 30, turn around and deceleration begins. Minutes 30 to 60, Return journey with same deceleration profile. Minute 60, landing, on your chronometer, 60 minutes exactly, the director says. On Earth's clocks, approximately 25 years and 17 days. Why 17 days, you ask? Rounding errors in the acceleration curves. Time dilation isn't linear. It increases exponentially as you approach light speed. 2 p.m., suit up. The flight suit feels heavier than during training. Or maybe that's just your mind playing tricks. 3 p.m., final walk to the transport vehicle. Rebecca and the kids are there. Behind a glass barrier, Emma presses her hand against it. You press yours against the other side. I love you, Daddy. I love you too, Princess. Take care of Mummy and Jake for me. For 1 hour, you swallow hard. Yes, for 1 hour, but you both know the truth. For her, it won't be 1 hour. It'll be 25 years. The transport vehicle pulls away. You watch your family shrink in the distance. Last time you'll see them at these ages. Last time Emma will be 7. Last time Jake will be 4. Last time Rebecca will be 33. The next time you see them, they'll be strangers wearing familiar faces. Launch sequence initiated. 3:45 p.m. You board Horizon 1. The spacecraft is smaller than you expected. 10 feet long, 6 feet wide. Just enough room for 1 seat, life support, and the revolutionary drive system. 3:55 p.m. Hatch seals, systems check. Green across the board. Mission control, Horizon 1. This is Houston. We are go for launch. T-minus 5 minutes. Your heart hammers. This is it. This is real. 4 p.m. exactly. Countdown begins. 10:98. You think about Emma's smile, Jake's laugh, Rebecca's touch. 3-to-1 ignition. The acceleration is smooth, surprisingly gentle. The drive system doesn't use chemical rockets. It manipulates space-time itself, pushes against the fabric of reality. You feel pressure, but nothing painful, nothing dangerous. The seat adjusts automatically to keep your body properly supported. 10 seconds in, velocity 8,000 miles per second, about 4% light speed. 20 seconds, 37,000 miles per second, 20% light speed. 30 seconds, 56,000 miles per second, 30% light speed. You look out the window. Earth is already distant. A blue and white sphere shrinking rapidly. 1 minute, 93,000 miles per second. 50% light speed. The stars ahead are changing color. The blue shift becomes visible. White stars turn pale blue. Blue stars turn violet. The entire forward view shifts toward the ultraviolet spectrum. Behind you, the opposite happens. Everything reddens. The universe hemorrhages color. 2 minutes, 149,000 miles per second, 80% light speed. Now things get weird. The universe ahead compresses. All the forward stars squeeze into a narrower and narrower cone. Your field of view collapses, like looking through a tunnel that keeps getting tighter. To your sides, complete darkness. Not because the stars disappeared, because their light can't reach you at this angle anymore. Relativistic beaming. Another consequence of moving at extreme speeds. 3 minutes, 167,000 miles per second, 90% light speed. Time dilation factor, 2.3, on Earth. 7 minutes have passed. Rebecca is probably driving home now. Emma asking questions from the back seat. Is Daddy in space yet? Yes, sweetheart. Will he send us messages? No, honey. He's moving too fast. approaching the edge. 5 minutes your time, 177,000 miles per second, 95% light speed, time dilation factor, 3.2. On Earth, 16 minutes have passed. Rebecca is home. She's probably sitting on the couch, staring at the mission clock on TV, watching the numbers tick up, knowing that each second for you stretches longer and longer for her. 7 minutes your time, 182,000 miles per second, 98% light speed, time dilation factor, 5. On Earth, 35 minutes have passed. 10 minutes your time, 184,000 miles per second, 99% light speed, time dilation factor, 7. On Earth, 70 minutes, over an hour. Emma is probably already in bed. Rebecca told her, "Daddy will be home in 1 hour." But an hour has passed. Emma is confused, upset. "Mummy, you said 1 hour?" Rebecca tries to explain. "For Daddy, it's 1 hour. For us, it's longer. How do you make a 7-year-old understand?" 15 minutes your time, 185,600 miles per second, 99.5% light speed, time dilation factor, 10. On Earth, 2.5 hours have passed. The stars ahead are now a brilliant pinpoint. Everything else is darkness. You're moving so fast that the universe itself seems to be collapsing into a single forward direction, and you feel normal. That's the strangest part. Your coffee in a special zero-spill container still tastes like coffee. Your breathing is steady. Your heart rate is elevated but not dangerously. You check your watch. 15 minutes. Exactly what it should be. But out there, time is racing forward. Maximum velocity achieved. 20 minutes your time. 186,100 miles per second. 99.9% light speed. Time dilation factor, 22. On Earth, 7 hours, 20 minutes have passed. It's 11:20 p.m. Rebecca is lying in bed, alone, staring at the ceiling. She's probably thinking about what the psychologist said. "He'll be fine. You'll be fine. It's just time." Just numbers, but they're not just numbers. They're moments, experiences, life. 25 minutes your time. You're at maximum velocity now. 99.995% light speed. Time dilation factor, approximately 72,000. On Earth, 12 years have passed. 12 years. Emma is 19. A college freshman, studying biology. She wants to be a doctor. She doesn't remember your face very clearly anymore. Just photos. Just videos. Jake is 16. High school. He plays basketball. He's good. Really good. College scouts are watching him. Rebecca is 45. She runs a pottery studio now. Found a creative outlet to deal with the grief, because that's what it is. Grief. Mourning someone who's still alive but unreachable. Your parents are elderly. Your dad had a heart attack 5 years ago. He survived. Barely. Your mum has arthritis. Moves slower. Talks about you in past tense sometimes. Catches herself. Corrects it. But the past tense feels more natural. And you've aged 25 minutes. You take a sip of coffee. Check the navigation display. Trajectory nominal. All systems green. In your subjective experience, this is a normal 30-minute flight. Smooth, uneventful, almost boring. Outside, civilizations could rise and fall in the time dilation gap. The turnaround, 30 minutes exactly. The ship's computer initiates turnaround sequence. The drive system reconfigures. Instead of pushing you forward, it starts slowing you down. The deceleration feels identical to the acceleration. Smooth, controlled, gentle, but deceleration at these speeds takes just as long as acceleration, and time dilation works the same way in reverse. 35 minutes your time, still traveling at maximum velocity. Beginning deceleration. On Earth, another 6 years pass. Total time, 18 years. Emma is 25 now. She's engaged, planning a wedding. Her fiancé is a teacher named David. Good man, patient, kind. Emma told him about you. My father is on a space mission. He'll be back someday, I think. Jake is 22, graduated college, playing professional basketball in Europe. He sends money home to Rebecca. He's a good son. Rebecca is 51. Grey hair, she doesn't bother dyeing anymore. She's accepted what this is. A different kind of widow. The uncertainty sometimes feels worse than death. At least death has finality. 40 minutes your time, 99% light speed now. Deceleration continuing. On Earth, 22 years total. Emma is 29, married, pregnant. Your grandchild growing inside her. A life you'll meet without context, without relationship. A baby who will call you grandpa but won't understand what that means. Jake is 26. He retired from basketball. Knee injury. Now he coaches high school kids. He's good at it. Patient, like someone taught him to be. Rebecca is 55. She dated someone for a few years. It didn't work out. She still wears her wedding ring. Habit, memory, promise. 50 minutes your time. 50% light speed. Earth coming into view. On Earth, 24 years total. Emma has a daughter. Her name is Sophie. 2 years old. Rebecca babysits twice a week. Those are her favorite days. Jake met someone, a physical therapist named Maria. They're moving in together. Your parents are gone. Your dad died 3 years ago. Your mum died last year. They never stopped hoping you'd return. Never stopped believing. 55 minutes, your time, 10% light speed, final approach. On Earth, 24 years, 11 months. Emma is planning a birthday party for Sophie's 3rd birthday. She wonders if you'll arrive in time. The mission clock says any day now, any hour now. Jake proposed to Maria. She said yes. Wedding planned for next summer. Rebecca stands in the pottery studio. Clay on her hands. She made you a cup. Blue glaze, your favorite color. She's made dozens over the years. Gives most away. But this one she'll keep. In case. 60 minutes. Landing sequence initiated. The ship descends through Earth's atmosphere. Heat shields glow. Retro rockets fire. Touchdown. Kennedy Space Center. Launchpad 39A. Same place you left from. Except everything looks different. Newer, older, changed. 60 minutes on your chronometer. Mission complete. Everything nominal. You unbuckle, stand, stretch, feel good, rested, alert. The hatch opens. Sunlight, warm December sun. Except it's not December anymore. It's January 2050. 25 years and 1 month since launch. A crowd waits. Hundreds of people. Cameras, reporters, scientists, and somewhere in that crowd, your family. You see her first. The grey-haired woman pushing through, Rebecca, your wife, except she's not the woman you kissed goodbye. She's 58 now. Lines around her eyes, age spots on her hands. Still beautiful, but different. It's really you, she whispers. Touches your face. You haven't aged a day. She's aged a quarter century. A young woman stands beside her. 32 years old, professional clothes, holding a toddler. "Dad," Emma says. The voice is familiar. The face is not. "This is your little girl." Except she's not little anymore. "Emma," your voice breaks. She nods, tears streaming. "You're exactly the same. Exactly like the videos. Exactly like I remember." The toddler squirms. "Who's that, Mummy?" "That's Grandpa," Emma says. "That's my daddy." A man approaches, tall, athletic, 29 years old. He has your eyes. "Jake?" you ask. "Hey, Dad." He tries to smile. It's awkward, painful. He was 4 years old when you left. He has almost no memory of you. You're practically a stranger. The weight of time. The crowd watches. This moment is historic. The first human to experience extreme time dilation and return. But for you, it's not historic. It's devastating. Your daughter is older than you now. Your son is an adult you never saw grow up. Your wife is approaching 60. And you had coffee 30 minutes ago. You're hungry for lunch. You need to use the bathroom. 1 hour ago, you kissed Emma goodnight. She was 7. Now she's 32, with a child of her own. 1 hour ago, Jake was building block towers. Now he's a former professional athlete and engaged to be married. 1 hour ago, Rebecca was 33, full of hope and fear and love. Now she's 58, weathered by time and waiting. "I'm so sorry," you whisper. "I didn't mean to be gone so long." Rebecca pulls you close. "You weren't gone long. We were. We're the ones who lived all those years. You just took a 1-hour flight." But that's the problem, isn't it? You didn't suffer. You didn't wait. You didn't watch years tick by wondering if you'd ever return. They did. Emma introduces you to Sophie, your granddaughter, 3 years old. She looks at you with curiosity but no recognition. "Can you tell her about me?" You ask Emma when she's older. Emma nods. "I will. I'll tell her everything." Jake's fiancée, Maria, approaches, shakes your hand. "I've heard a lot about you. All good things, I hope." You try to joke. She smiles politely, but there's a distance there. How could there not be? You're her fiancé's father, but you're also a stranger who hasn't existed in their relationship. The mission director approaches. "We need to debrief. Medical examinations, data analysis." You nod. Turn to your family. "I'll see you later." "We'll be here," Rebecca says. We've gotten good at waiting. The words sting. Not because she meant them to, because they're true. You follow the mission director toward the medical facility. Turn back once. Your family watches, waving. They lived 25 years in the time it took you to drink a cup of coffee. And nothing can ever give those years back. This is what time dilation means in human terms. Not equations, not graphs, not theoretical calculations. Loss, displacement, disconnection. You traveled faster than almost anything in the universe. You pushed the boundaries of physics. You achieved something incredible, but the cost, your daughter's childhood, your son's adolescence, your wife's youth, your parents' final years. Can knowledge justify that? Can exploration redeem it? Can humanity's future balance against one family's sacrifice? These aren't abstract questions anymore. They're real, personal, painful, and in the next section, we'll examine why this happens. Not just how, but why the universe is structured this way. What forces space and time to behave like this? What's the deeper truth beneath the mathematics? And is there any way around it? Part 4. Scientific explanations and paradoxes. Now that you've lived through the experience, felt the emotional weight, witnessed the reunion that breaks your heart, let's understand why. Not just Einstein said so, not just the math works out, but why the universe must behave this way. Why time dilation isn't just a quirk of physics, but a fundamental feature of reality itself. Because here's the thing, the universe doesn't care about our feelings. It doesn't care about families torn apart by temporal displacement. It follows rules, deep, unbreakable rules, and once you understand these rules, time dilation stops being mysterious. It becomes inevitable. Space-time, the fabric that binds everything. Let's start with the most important concept, space-time. Before Einstein, we thought space and time were separate. Space was the stage. Time was the clock. They didn't interact. They just coexisted. Einstein showed us we were wrong. Space and time are woven together. They're not separate entities. They're different aspects of the same thing. Space-time, think of it like a fabric, a four-dimensional fabric. 3 dimensions of space length, width, height, and 1 dimension of time. When you move through this fabric, you're moving through all 4 dimensions simultaneously. Always. Even when you think you're sitting still. But I'm sitting still right now. You say no, you're not. You're sitting still in space, but you're moving through time, 1 second per second, advancing into the future at a steady rate. That's movement through the time dimension. Now imagine you start moving through space. You stand up, walk across the room, 5 miles per hour. Your total velocity through space-time hasn't changed. It's still constant, fixed, locked at the speed of light. But now you're splitting that velocity between 2 directions. Most of it still goes toward time movement. A tiny bit goes toward space movement, which means your time movement must slow down. Just a little, imperceptibly little, at 5 miles per hour. But it does slow down. This is the key insight. Your velocity through space-time is constant. Always. For everyone. Everywhere. The speed of light isn't just the speed limit for traveling through space. It's the speed everyone travels through space-time. All the time. When you move faster through space, you must move slower through time. The universe has no choice. The math demands it. The mathematics of space-time geometry. Scientists describe this with something called the space-time interval. It's a measure of separation between 2 events in space-time. The formula involves squares and square roots, but the concept is simple. Distance through space and distance through time combine in a specific way, and here's the critical part. The space-time interval is the same for all observers. It's invariant, unchanging. You might measure more time and less space. I might measure more space and less time. But when we calculate the space-time interval, we get the same answer. This is what Einstein meant by relativity. Not that everything is relative, that some things are absolute. The speed of light is absolute. The space-time interval is absolute. The laws of physics are absolute, but time and space individually, those are relative. They depend on your motion, your reference frame, your perspective. Let me give you an example. 2 spaceships pass each other. Ship A travels at 50% light speed relative to Earth. Ship B travels at negative 50% light speed relative to Earth. From Earth's perspective, the ships are moving apart at 100% light speed combined. But from Ship A's perspective, Ship B isn't moving at 100% light speed. It's moving at 80% light speed. Wait, You say 50 plus 50 equals 100. Basic math, not in space-time. Velocities don't add the way we expect. They add according to the relativistic velocity addition formula. The faster you go, the less additional velocity you can add. It's asymptotic, approaching light speed, but never reaching it. This isn't a limitation of engines or energy. It's a limitation of space-time geometry. You can't move through space-time faster than light speed, not because we haven't figured out how, because it's geometrically impossible. Like asking what's north of the North Pole. The question doesn't make sense. There is no north of the North Pole. Similarly, there is no faster than light speed. Not anywhere in the universe. Length, contraction. Space shrinks, too. Time dilation has a twin effect. Length contraction. When you move fast, distances shrink. In the direction of motion, space compresses. From your perspective on Horizon 1 traveling at maximum velocity, the distance to your destination isn't what Earth measures. It's shorter, much shorter. Let's say you're traveling to a star 10 light-years away at 99.995% light speed. From Earth's perspective, distance is 10 light-years. Your travel time is about 10 years. From your perspective, distance is about 140,000 miles. Your travel time is about 30 seconds. Same journey, different measurements, both correct within their own reference frames. But which measurement is real, you ask? Both. That's the point. Reality depends on the observer. There's no universal truth about distance or time, only relative truths, frame-dependent truths. This bothers people. It bothered Einstein initially. It bothers physicists even today. We want the universe to have one true state, one correct answer, one objective reality, but the universe doesn't work that way. Objectivity exists for invariant quantities, the space-time interval, the speed of light, the laws of physics, but space and time individually, flexible, malleable, observer-dependent. The twin paradox resolved. Remember Marcus and Diana, the twins from part 2. Diana travels at extreme speed for 10 years her time, returns home. Marcus has aged 20 years while Diana aged 10 years. Someone always asks, from Diana's perspective, Marcus was moving, so shouldn't Marcus be younger? This is the twin paradox. Except it's not actually a paradox. It's a misunderstanding of relativity. Here's the key. Special relativity only applies to inertial reference frames. That means constant velocity, no acceleration, no turning around. Marcus stays on Earth. Roughly constant velocity. Yes, Earth orbits the Sun and rotates, but we're ignoring that for simplicity. Diana accelerates, reaches high speed, decelerates, turns around, accelerates back, decelerates to land. All that acceleration breaks the symmetry. When Diana accelerates, she's no longer in an inertial reference frame. Special relativity doesn't fully apply. General relativity takes over. And general relativity says, the person who accelerates ages less. Not because acceleration directly affects aging, because acceleration reveals who changed reference frames. Think of it this way. Marcus stays in one reference frame the whole time. Diana switches between multiple reference frames. All that switching costs time. This has been tested experimentally, multiple times, with atomic clocks, with particle decay rates, with GPS satellites. Every single test confirms the person who accelerates ages less. Not a paradox. An asymmetric situation with a definitive answer. Why can't we go backward? If we can slow down time, people ask, can we reverse it? Can we travel backward through time? No, here's why. Time dilation lets you move forward through time faster. From your perspective, time flows normally, but compared to others, you skip ahead. To reverse time, you'd need to move faster than light, exceed that cosmic speed limit, and as we've established, that's impossible. Not technologically impossible, geometrically impossible. The mathematics of spacetime forbids it. Think about the Lorentz factor. As your velocity approaches light speed, the factor approaches infinity. Time slows down more and more dramatically. At exactly light speed, the factor becomes infinite. Time stops completely. This is why photons don't experience time. From their perspective, their journey is instantaneous. To go backward, you'd need to exceed light speed, which would require the Lorentz factor to become imaginary. An imaginary number, not real. The math breaks. The physics breaks. Reality breaks. Some physicists have theorized about exotic solutions, wormholes, Alcubierre drives, closed time-like curves. These are mathematical possibilities. Like dividing by zero gives you infinity. Mathematically valid, physically meaningless. Every realistic analysis shows these solutions require negative energy, exotic matter that probably doesn't exist. Amounts of energy greater than the entire universe contains. In other words, don't hold your breath for a time machine. Forward only. That's the deal. Gravity does it too. Time dilation isn't just about velocity. Gravity causes it as well. The stronger the gravitational field, the slower time flows. On Earth's surface, time moves slightly slower than at high altitude. GPS satellites orbit at 12,500 miles up. Gravity is weaker there. Time moves faster. The difference? About 45 microseconds per day. Combine that with the velocity time dilation, which makes satellite clocks run slower, and the total correction is about 38 microseconds per day faster. This is gravitational time dilation, predicted by Einstein's general relativity, confirmed by experiment. Near a black hole, the effect becomes extreme. Close to the event horizon, time nearly stops relative to distant observers. Fall toward a black hole, and from your perspective, everything seems fine. You cross the event horizon in finite time, but from an outside observer's perspective, you never cross. You slow down, asymptotically approach, but never reach the boundary. Both perspectives are correct. Both are real, just different reference frames. Some science fiction stories use this. Send astronauts near a black hole. They experience a few hours. Earth experiences decades. Same time dilation principle, different cause, same result. The cosmic speed limit is universal. Let's address something important. Why is the speed of light the cosmic speed limit? Why not faster? Why not slower? Why that specific number? The answer involves deep physics, the structure of space-time, the nature of causality. Light speed isn't really about light. It's about information, cause and effect. The maximum rate at which anything can influence anything else. If you could send signals faster than light, you could violate causality, send messages to your own past, create paradoxes, break the logical consistency of the universe. The universe doesn't allow this, can't allow this. The mathematics forbids it. Light speed is the speed of causality, the speed of information, the maximum rate at which effects propagate. Photons travel at this speed because they're massless. Anything with mass travels slower, must travel slower. The mass itself prevents reaching light speed. As you accelerate something with mass toward light speed, its effective mass increases. The energy required to accelerate it further increases exponentially. To actually reach light speed would require infinite energy, which doesn't exist. So massive objects always travel slower than light. Massless particles always travel at exactly light speed. Nothing travels faster. This isn't an engineering problem. It's a structural feature of reality. Real-world applications beyond GPS. Time dilation affects more than just GPS and cosmic rays. Particle accelerators use it constantly. When physicists accelerate particles to 99.99% light speed, those particles live longer. A particle that normally decays in 1 microsecond might live thousands of microseconds when moving fast. This gives scientists time to study it, measure it, understand it. Without time dilation, much of particle physics would be impossible. We couldn't study short-lived particles, couldn't run many experiments, couldn't learn what we've learned about fundamental forces. Astronomy uses it too. When we observe distant galaxies moving away from us at relativistic speeds, we have to account for time dilation. Their light is redshifted, not just by motion, but by the time dilation of their atoms. Even chemistry is affected. Electrons in heavy atoms move at significant fractions of light speed. Time dilation and length contraction affect their behavior. This is why gold is gold-colored instead of silver. Why mercury is liquid at room temperature. Relativistic effects on electron orbitals. Time dilation isn't some exotic effect that only matters in extreme situations. It's woven into the everyday behavior of matter and energy throughout the universe. The question that haunts everyone. So here's what keeps people up at night. If time isn't universal, if different observers experience different durations, what does that mean for free will? Think about it. From your perspective on Horizon 1, you travel for 60 minutes. You make decisions. You think thoughts. You experience moments. But from Earth's perspective, those 60 minutes are 25 years. Does your free will operate on your timeline or Earth's timeline? When you decided to turn around at the 30-minute mark, was that decision made at minute 30 for you or year 12 for Earth? The answer: both. Simultaneously, the decision exists in space-time. It has a specific space-time coordinate. Every observer agrees the decision happened at that coordinate. They just disagree about when was. Free will isn't about absolute time. It's about causality. You made the decision based on information available to you. The decision caused subsequent events. The causal chain is unbroken. Causality is preserved. Free will is preserved. Only our intuitive notion of simultaneous time is lost. And maybe that's the hardest part. We feel like there should be a universal now, a single moment that is the present for everyone, everywhere. But there isn't, never was. We just moved slowly enough that we never noticed. The universe doesn't negotiate. Here's the brutal truth. The universe doesn't care about our convenience. It doesn't care about keeping families together across temporal dimensions. It doesn't care about our desire for simple, intuitive physics. The rules are the rules. Space-time geometry is what it is. The speed of light is constant. Time dilation follows inevitably from these facts. You can accept it or reject it. But rejection doesn't change reality. Every experiment confirms it. Every measurement supports it. Every application proves it works. Time dilation is as real as gravity, as real as electromagnetism, as real as the atoms in your body. And if humanity wants to explore the cosmos, we must accept this reality, plan for it, design around it, embrace it. because the stars aren't going to come to us. We have to go to them, and when we do, when we finally build ships capable of reaching relativistic speeds, we'll face the same choices our hypothetical astronaut faced. Trade time for distance. Trade relationships for exploration. Trade home for the stars. Some will make that trade gladly. Pioneers, explorers, people who value discovery over stability. Others will refuse. Choose Earth. Choose family. Choose the slow, steady march of normal time. Neither choice is wrong. Both are valid. But everyone must choose. Because time dilation doesn't compromise. It doesn't offer halfway solutions. It doesn't bend the rules for exceptional cases. You move fast. You lose time. Period. We've journeyed deep into the mechanics, the mathematics, the paradoxes that aren't really paradoxes. We understand why time dilation happens. Not just that it happens, but why it must happen. Why the universe has no alternative. Why the geometry of space-time demands this trade-off between space and time. But understanding doesn't make it easier. Knowing the physics doesn't heal the emotional wounds. Calculating the Lorentz factor doesn't reunite separated families. So in our final section, we need to confront the biggest questions of all. What does this mean for humanity's future? Can we build a civilization that spans the stars despite time dilation? Should we even try? And if we do, what kind of people will we become? The message from tomorrow. But here's something to consider right now as you process this information, as you wrestle with these implications. Time dilation is happening, not dramatically, not at relativistic speeds, but it's happening. Particles in cosmic rays, satellites in orbit, electrons in atoms, all experiencing time at different rates than you. The universe has been doing this forever. We just noticed recently, and maybe that's the real message. The universe doesn't wait for our permission. It doesn't stop for our comfort. It just is. Time dilation exists, will always exist, can't be wished away or legislated out of existence. Our only choice is how we respond. Do we fear it, avoid it, hide from the implications, or do we embrace it, lean into it, accept it as part of reality and build our future around it rather than against it? History suggests humans are pretty good at adaptation. We've survived ice ages, plagues, wars, famines, disasters of every kind. We've crossed oceans that seemed uncrossable, climbed mountains that seemed unclimbable, solved problems that seemed unsolvable. Maybe time dilation is just the next challenge, the next seemingly impossible barrier that we'll eventually treat as routine. In 300 years, maybe people will board ships for interstellar journeys the way we board airplanes. Today, casually, confidently, without existential dread, they'll say goodbye to loved ones, knowing they won't see them again. But they'll have made peace with that, developed rituals and frameworks and support systems that make it bearable. They'll be different humans than we are, adapted to temporal displacement the way we're adapted to international travel. Or maybe not. Maybe it'll always hurt, always cost something irreplaceable, always require sacrifice that tears at the soul. But they'll do it anyway, because the stars call, because curiosity demands, because humanity has never been able to see a frontier without crossing it. The final question. So here we are, at the end of 90 minutes together, you and me, moving through time at the same rate, sharing this moment, this experience, this revelation about the nature of reality. In those 90 minutes, muons have been created and destroyed thousands of times over. GPS satellites have experienced microseconds of time dilation. Particles in accelerators have lived extended lives due to relativistic speeds. The universe has been demonstrating time dilation constantly. We just haven't been moving fast enough to notice. But someday we will. Someday someone will board that ship, reach those speeds, experience those effects personally. And when they return, aged 1 hour while Earth aged 25 years, they'll carry a message. Time isn't what we thought. Reality isn't what we imagined. The universe is stranger and more beautiful and more terrible than our ancestors could have conceived. But it's also navigable, understandable, survivable. We can explore it, master it, thrive in it, if we're brave enough, if we're wise enough, if we're willing to pay the price. The question is, are we? One more thing before we go. There's a spacecraft being designed right now. Breakthrough a project to send tiny probes to Alpha Centauri at 20% light speed. They won't carry humans, just cameras, instruments, data collection systems. They'll arrive in 20 years. Send back images, information, proof that we can reach another star system. And when those images arrive, when humanity sees the planets of Alpha Centauri for the first time, something will shift. The stars won't be abstract anymore. They'll be places, real places, reachable places. And someone, somewhere, will start building the next ship. The bigger ship. The human-carrying ship. The ship that makes time dilation personal. That person might be watching this right now. Might be you. Might be your child. Might be someone not yet born. But they're coming. They're inevitable. They're written into humanity's future as surely as time dilation is written into space-time's structure. And when they launch, when they accelerate to extreme relativistic speeds, when they return decades or centuries later having aged only hours, they'll prove everything we've discussed today. Not theoretically, not mathematically, not experimentally, but experientially, viscerally, undeniably. They'll be living proof that time is relative, that the universe is stranger than we imagined, that the price of the stars is measured in years we'll never get back. Will you be there to see it? Will you live long enough to witness humanity's first temporal explorer return home? Or will you be the explorer yourself, stepping off that ship into a world that moved on without you? Either way, the journey has already begun. Time dilation isn't coming, it's here. It's always been here. We're just now catching up to what the universe has been trying to tell us all along. Time is relative. Space is flexible. The cosmos is vast, and the only limits are the ones we accept. So what will you accept? What limits will you honor? What boundaries will you cross? The stars are waiting. Time is passing. The choice is yours. But remember, however you choose, time keeps moving. For some of us, slower. For others, faster. But always forward, always onward. Always into the unknown. Thanks for taking this journey with me. Thanks for wrestling with these impossible questions. Thanks for imagining a future where humanity reaches for the stars, knowing the cost, and reaches anyway. In 90 minutes, we've traveled through the deepest mysteries of space-time. We've confronted the mathematics that break our hearts. We've stared into the temporal abyss and asked, is it worth it? I don't have the answer. Neither does anyone else. Not yet. But someday, someone will answer with their life, their choices, their sacrifice. And on that day, humanity will know. Until then, we wait, we wonder, we prepare. Because the universe doesn't wait for us to be ready. It just is. One last thought. Right now, there might be civilizations out there, Advanced aliens who mastered relativistic travel millennia ago. They might be watching us, waiting to see if we figure it out, waiting to see if we make the leap, waiting to see if we're willing to pay time's price for space's reward. If they're watching, what do we want them to see? A species too afraid to leave home, too attached to comfort, too unwilling to sacrifice for discovery? Or a species brave enough to face the impossible, wise enough to understand the cost, determined enough to reach for the stars anyway? The answer will define us, not just as individuals, as a species, as a civilization, as a chapter in the universe's story. So choose carefully, choose bravely, choose with full knowledge of what time dilation means and demands, and then live with your choice. Because in the end, that's all any of us can do. See you in the next one, whenever next happens to be.